Hello viewers, welcome to my channel. I'm Hasham Ali Khan. Last three problems I have completed on maximization type problems. So in simplex model we have four types of problems: maximization, minimization, mixed constraints and duality. The first maximization problem. In maximization problem, slack variable will be added and the constraints are of less than equal to type. For minimization problem, the constraints will be greater than equal to type. In this case, we have to subtract the surplus variables and add artificial variables. Remaining calculations are same. So here I am going to start the fourth problem. Before starting the fourth problem, I expect my viewers to have a printout of the problems which I have given in the link under my description. Without having problems, you cannot understand my explanation. So take the screenshot of the points, then I'll explain all the points in detail. Come on, see the fourth problem. A chemical company produces two compounds A and B. The following table gives the units of ingredients C and D per kilogram of compound A and B, as well as requirement of C and D and cost per kilogram of A and B. Actually, the decision variables are, we have to find out how many units of compound A and B to be produced. For making this compound, we have two resources, two ingredients. The ingredients are C and D. So we are having a maximum limit of ingredients. Requirement of C and D. Using the simplex method, find the quantities of A and B which would give a supply of C and D at a minimum cost. So problem it is given, the objective is minimum of cost. So the ingredients are C and D, compound A and B. For making 1 unit of compound A, we need 1 unit of ingredient C and 2 units of ingredient C for B product. And minimum requirement is 80. Minimum requirement means we can use more than 80, but minimum is 80, not less than 80. Similarly, D, ingredient D, 3 units are required for making 1 unit of compound A, and 1 unit of D is required for making 1 unit of compound B. And the minimum requirement is 75, not less than 75. We can use 75 or more. Cost per kilogram of compound A is 4 and B it is 6. That's it. So first of all, we suppose let X1 be the number of units of compound A to be produced, and X2 is the number of units of compound B to be produced. That X1 and X2, these are the decision variables. We have to find out X1 and X2. The objective is to minimize the cost. Then formulation of LPP. First of all, we have to formulate the linear programming problem in a mathematical model. Consists of 3 parts. The first part is objective function, second subject to constraints, and third non-negativity restriction. First of all, objective function, minimization of cost. Minimize cost, Z is equal to. What is the cost per kilogram of A compound? Cost per kilogram 4. And here it is 6. How many units of A we are making? X1. So 4X1 is the total cost of compound A. Similarly, the cost per unit of compound B is 6. So 6X2. This is the objective. Now subject to constraint. What are the limitations? First, ingredient C. We require 1 unit for A and 2 units for B. So 1X1 plus 2X2. So X1 plus 2X2. The minimum requirement is 80. Minimum, not less than. It should be 80 or more. So greater than or equal to 80. Second constraint, D ingredient. 3X1 plus X2 should be greater than or equal to 75. 3X1 plus X2 greater than 75. And non-negativity restriction says the X1 and X2 should always be 0 or more, but not less than 0. There cannot be negative production. So x1 and x2 greater than or equal to 0. This is the formulation of LPP. Now, for minimization problem, remember the point. And I suggest my viewers, my students always to keep a notebook, calculator, pen ready. Whenever I say important points, note it down. Then only you can be able to get the good command. In the whole operation research subject, this is the most time consuming problems. If you are, perfect in calculations, in remembering the rules, then your time will get reduced. Within the stipulated time, we can complete the question paper. Otherwise, lot of time is required if you practice in examination. So beforehand, now itself, you should make the practice. So what are the rules for minimization problem? For minimization problem, the constraints are greater than type. This is the greater than. Previous three problem you have seen for maximization problem, we have less than equal to type. But here we have greater than equal to type. So we subtract the surplus variable S1 and S2. How many constraints we have? Two constraints. So S1 and S2 should be subtracted, minus S1 and minus S2. We add artificial variable. See here, if we take minus S1 and minus S2, that means S1 and S2 will become negative. But it should not be negative. So to remove that constraint, we add artificial variable A1 and A2. In maximization type, we have only slack variable added. In minimization type, we subtract the surplus variable and add artificial variables. The standard form of LPP will then become like this. So objective function minimize z is equal to 4x1 plus 6x2. Now here we have to add the surplus and artificial variable also. For surplus variable, 0 coefficient. What we have done in maximization problem, 0 into S1 plus 0 into S2. But the coefficient of artificial variable is plus m. Remember this point. Note it down immediately. Plus m is the coefficient for artificial variable. And when we take plus m, when the problem is minimization. When minimization problem, plus ma1 plus ma2. Now subject to constraint. The first constraint x1 plus 2x2 minus s1 plus a1. Minus s1 plus a1. Now this inequality is removed. By introducing the surplus and artificial variable, the inequality will be converted into equality. Equation is equal to 80. Similarly, 3x1 plus x2 minus s2 plus a2 is equal to 75. And non-negativity restriction says all the variables should be more than or equal to 0. x1, x2, s1, s2, a1, a2. All the values should be greater than or equal to 0. This is the standard form of LPP to find the solution by simplex. Now, an initial solution is obtained by taking x1 is equal to 0, x2 is equal to 0. S1 is equal to 0 and S2 also equal to 0. Then ultimately what it will remain? A1 is equal to 80 and A2 is equal to 75, because all these values are going to become zeros. So A1 is equal to 80, A2 is equal to 75. By taking this, we start our iteration by simplex table 1. Simplex table 1 is very easy to make because we don't require any formulae. Simply we take the coefficient. The table will be same what we have done in the maximization type of problems. First of all, simplex table, Cj stands for coefficient of objective function. Cj is there in the row and also Cj is there in the column. The basic variables currently is A1 and A2. A1 is 80 and A2 is 75 here, right? Now, for this body of this matrix, here the coefficient of objective function are x1 is equal to 4, x2 is equal to 6. Then s1 is 0, s2 is 0, a1 is m, a2 is m, right? Now, for this body of this matrix, we take the coefficient of constraint. The coefficient are 1x1, so I am writing 1 here. Then 2x2, 2 I am writing. S1 is minus 1. S1 means 1 S1. So minus 1. So S1 is minus 1. And A1 is plus 1. So A1 plus 1. Other values we will take zeros. Second constant 3x1. So x1 3. And 1x2. x2 is 1. S2 is minus 1. S2 is minus 1. And A2 is 1. A2 is 1. Remaining values will take zeros. That's all. So this is the body of the first table. Now as usual we calculate Zj, multiply the Cj with these values. M into 80, 80M. M into 75, 75M. So 80M plus 75M. If you add up 80 plus 75, 80 plus 75, you will get 155M. 155M is the Zj value. Now 1M, 1 into M is 1M. M into 3 is 3M. So 1M plus 3M, it comes to 4M. Right? Then M into 2, 2M. Plus 1 into M, M. 2M plus 1M, 3M. Here, M into minus 1 is minus M. And M into 0 is 0. So here we write minus M. Here M into 0 is 0. M into minus 1 is minus M. Here M into 1 is M. And M into 0 is 0. So plus M. Here also M into 0, 0. M into 1 is M. That's all. So we have calculated the Zj value. The next thing is we have to find out the Cj minus Zj. Here Cj is on the top and Zj is 4 minus 4m. 4 minus 4m. Similarly 6 minus 3m. 6 minus 3m. Here 0 minus minus m. Already minus is there. So Cj minus Zj, 0 minus minus m. So minus into minus will become plus. So 0 plus m, it will become m. Here also 0 minus minus m plus m. M minus m 0, m minus m 0. That's all. So we have calculated the Cj minus Zj values. Right? Now, optimality test. In maximization type of problems, we have seen that all the index row elements should be zeros and negative. The highest positive was selected in the previous problem. But in this minimization problem, the optimality test is all the index row elements should be zeros and positives. If there is any negative value, it is not optimum. We have to go for another table. Another table. In that case, most negative value we have to select. Then how to find out without m? When m is there, we don't know what is the value of m. How we can be able to know whether it is positive or negative? Here, we have to suppose, let m is equal to 10. So any value you can substitute m is equal to, provided this value should be more than the actual cost of x1 and x2. What is the actual cost of x1? 4. Actual cost of x2 is 6. So any value you can take which is more than 4 and 6. So for easy calculations I have taken 10 because easily we can multiply, right? If it is 16 here, you cannot take 10 because the m value should be greater than this x1 and x2 value, right? Now, suppose first case, here it is 4 minus 4m, 4 minus 4 into 10, so 4 minus 40, it is minus 36. We are getting minus 36. Second, 6 minus 3m, that means 6 minus 3 into 10, 6 minus 30, it is minus 24. So if we suppose m is equal to 10, the first value, this value we are getting minus 36 and this value we are getting minus 24. All the values should be positive and zeros. There should not be any negative, but we are having two negative values. So it is not optimum. We have to prepare another table, right? So which is the most negative here? minus 36 is the most negative. So minus 36 is for this one. So this is the entering variable in the next iteration. Next table, x1 will enter. Now which item will depart? It depends on the minimum ratio. As usual, solution value divided by intersectional element. What is the solution value here? 80. 80 divided by 1. 80 divided by 1 is equal to 80. Here 75 divided by 3. 75 divided by 3 is equal to 25. So we have calculated minimum ratio. So select the minimum value in these ratios. Minimum is 25. So for which variable 25 it is there? A2. So in the next iteration, A2 will depart. A2 will go away. In place of A2, which variable will enter? X1. So here I am writing X1 enters and A2 departs. And one more point you remember and note it down. When artificial variable is departed, no need to open the column. Here we have x1, x2, s1, s2, a1, a2. Now a2 is departed. So no need to make a2 column in the next table. Only a1 is required. So here I have taken a1. x1, x2, s1, s2, a1. That's it. Right? Now the basic variable a1. This a1 will remain as it is. Now in place of a2, we are writing x1. The coefficient of a1 is m. The coefficient of x1 is 4. That's all. Now we need the values of the entering variable. Same formula we apply what we have done in the previous problems. So values of entering variable. Entering variable. The entering variable is x1 is equal to values of departing variable. Values of departing variable is a2 divided by intersectional element. Same formula what we have done in previous problems. Intersectional element. Now what are the values of a2 here? 75. Then next one 310. 310. 310 minus 1 and 0. I am not taking this one because in our table A2 is departed. A2 column is not there. We have only column up to A1. So we will take up to this one. 75, 3, 1, 0, minus 1, 0. Divided by intersectional element. What is the intersectional element here? 3. Divided by 3. So 75 divided by 3 is 25. 3 divided by 3, 1. 1 divided by 3, 1 by 3. 0 by 3, 0. Minus 1 by 3, that is 0. That's all. We got the values of the entering variable x1. So here x1 I am writing the value 25. 1, 1 by 3, 0, minus 1 by 3 and 0. That's all. So we got the values of the entering variable. Now values of A1. Values of A1 is equal to old values of A1 as usual minus intersectional element into values of entering variable. Same formula what we have applied in maximization type of problems. So values, old values of A1 are 80, then 1, then 2, minus 1, 0 and 1. We are not taking the value of A2 because we don't have the column of A2. Minus intersectional element of A1. A1 intersectional element is 1. 1 into. Now values of the entering variable. Entering variable value 25. Then 1. 1 by 3. Then 0. minus 1 by 3 and last one 0 is equal to. Now 80 minus 25. So we can calculate 80 minus 25, it comes to 55. Then 1 minus 1, 0. 2 minus 1 by 3. So if we take the LCM 3 2s are 6. 3 gets cancelled 1. So it will become 5 by 3. Minus 1 minus 0, it will be minus 1. 0 minus into minus will become plus 1 by 3. 0 plus 1 by 3 is 1 by 3. 1 minus 0 is 1. That's all. These are the values of A1. What are the values? 55, 0, and then 5 by 3. Then we have minus 1, then 1 by 3, and lastly it is 1. So we have calculated the values of A1, right? Now we need the values of Zj. To multiply m into 55 is 55m. 4 into 25 is 100. So we can write down 100 plus 55m. 100 plus 55m. Right? Similarly, m into 0 is 0. 4 into 1 is 4. That's all. Now next one. M into 5 by 3 is 5m by 3. Plus 4 into 1 by 3 is 4 by 3. If we take the LCM, 5m plus 4 by 3. 5m plus 4 by 3. So here you write down 5m plus 4 divided by 3. So m into minus 1 is minus m. 4 into 0, 0. So here you can write minus m. Here m into 1 by 3 is m by 3. M into 1 by 3 is m by 3. Plus into minus will become minus. 4 into 1 by 3 is 4 by 3. LCM if we take 3, so m minus 4 by 3. M minus 4 divided by 3. So here m into 1 is m. 4 into 0 is 0. So m remains. So we got the values of Zj. Now Cj minus Zj. So here 4 minus 4, 0. Then 6 minus. So simply write down 6 minus 5m plus 4 divided by 3. Here 0 minus into minus m. So 0 minus minus m will become plus m. See here. 0 minus into minus m. So minus into minus will become plus. 0 plus m is m. That's all. Here we have calculated. Now this one 0 minus. Here we are calculating Cj. So 0 minus m minus 4 divided by 3. That's it. So here m minus m is 0. That's all. We got the values of Cj minus Zj. Now optimality test says all the Cj minus Zj, that is the index row elements. These index row elements should always be zeros and positives. For this type of problem, minimization type, zeros and positive. If any negative value is there, it is not optimum. We have to make another table. So here we'll check. Let m is equal to 10. M is equal to 10. Because 10 is greater than 4 and 6, that's why I am taking 10. Right? You can take 20, 30, 40, 100, any value. But it should be more than 4 and 6. That's it. Now, for this value, 6, first one, 6 minus 5m plus 4. 5m plus 4 divided by 3. This is the value. This is the value of Cj minus Zj. So 6 minus 5 into 10. 5 into 10 is 50. 50 plus 4, 54 by 3. So 6 minus 54 by 3. 6 minus 54 divided by 3 is equal to 18. So 6 minus 18, it is minus 12. 6 minus 18 is equal to minus 12. So we got this value minus 12. Now secondly 0 minus m minus 4 by 3. M minus 4 divided by 3. 0 minus m is 10. 10 minus 4 is 6. 6 divided by 3 is 2. So 0 minus 2 is minus 2. Now see here. Which variable is most negative? Minus 12 is most negative. So this value minus 12 means 6 minus 5m plus 4. This value. This is the most negative. This is the entering variable in the next iteration. So here I am putting this arrow mark, and these are the intersectional element, and x2 will enter in the next table. x2 will enter. Now which variable will depart? Depends on minimum ratio. Solution value divided by intersection variable. Solution value 55. 55 divided by 5 by 3. 55 divided by 5 by 3. Now see here. 55 divided by 5 by 3 can be written as 55 into 5 by 3 can be written as 3 by 5. Because when division is converted into multiplication, it will become inverse. So 5 by 3 will become 3 by 5. So 5 ones are 5, 5 11s are 55, 33. So here you are getting 33. Right? Here 25 divided by 1 by 3. 25 divided by 1 by 3. So we can make reciprocal. 25 divided by 1 by 3 is equal to 25 into 3 by 1. Reciprocal. So 25 into 3 is 75. 75. That's all. Now minimum of these 33 or 75. Whichever is less. 33 is less. So this is the departing variable. So which variable will depart? A1 will depart. In the next table, A1 will depart and X2 will enter. And remember, once the artificial variable is departed, no need to open the column. In the next table, we need only X1 column, X2 column, S1 column, S2 column. A2 already departed, and now A1 is also being departed. So we have completed 2 tables. Now we have to make table number 3. See, now we are making simplex table 3. Already second table we have prepared, and X2 will enter, A1 will depart. So here you can see simplex table 3, X2 enters and A1 departs. So in place of, I have not opened the column of A1 and A2 because A1 and A2 have departed. Now we need only X1, X2, S1, S2. No artificial variable will exist. Now, first X2 enters. So we need the value of entering variable X2. So values of entering variable X2 is equal to values of departing variable. Which variable is departing? A1. So values of departing variable divided by intersectional element. So values of departing variable are 55, then 0, 5 by 3, minus 1, 1 by 3. I am not taking the value of A1 because A1 is departed. No column for A1. Right? So here 55, 0, 5 by 3, minus 1, 1 by 3. And intersectional element is 5 by 3. So 55 divided by 5 by 3. So if we make it multiplication instead of division multiplication, this will become inverse. 5 by 3 will become 3 by 5. 5 ones are 5, 5 11s are 55. So 11 3s are 33. Then similarly 0 divided by 5 by 3, 0. 5 by 3 divided by 5 by 3, 1. Minus 1 divided by 5 by 3. So minus 1 can be written as minus 1 by 1 into 3 by 5. So what it will become? Minus 3 by 5. Similarly 1 by 3 divided by 5 by 3. So 1 by 3 into 3 by 5. So 3 will get cancelled, 1 by 5. So we got the values of the entering variable X2. So take down these values of X2, 33. Here 33, next one 0, 1, minus 3 by 5 and then 1 by 5 over. We got the values of entering variable X2. Now we need the new values of X1. So formula same, values of X1 is equal to old values of X1. Which are the old values of X1? Here 25, 1 minus 3, 1 by 3, 25, 1, 1 by 3, 0 and minus 1 by 3. I am not taking 0 value because A1 is departed, right? Minus intersectional limit. What is the intersectional limit here? 1 by 3. So 1 by 3 I have taken into values of entering variable. Entering variable values are 3301. So 3301, 1 by 5, 3 by 5 and 1 by 5. Minus 3 by 5 and 1 by 5. I have taken. Now simplify. 33, 1 by 3 into 33 is 11. So 25 minus 11 is 14. Similarly, 1 by 3 into 0 will be 0. So 1 minus 0, 1. 1 by 3 minus 1 by 3 is 0. So 0 minus into minus will become plus. 3 will get cancelled. 1 by 5 remains. So minus 1 by 3 minus 1 by 3 into 1 by 5 is 1 by 15. So minus 1 by 3 minus 1 by 15. So if we take the LCM 15, 3 how many times cuts 15? 5 times. So 5 ones are 5, minus 5. 15 how many times cuts 15? 1 time. 1 into 1 is 1. So minus 5 minus 1 is minus 6. We are not multiplying, remember, we are not multiplying minus into minus. We are simply adding up the minus signs. So minus 5 minus 1 is minus 6. Minus 6 by 15, or it is divisible by 3. So 3 2s are 6, 3 5s are 15. Minus 2 by 5. These are the new values of x1. What are the values? 14. Next one is 1 0, 1 0. Then 1 by 5. And lastly it is minus 2 by 5. That's it. So we have calculated all the values of x1 and x2. Now zj value. Multiply the coefficient of objective function into value. So 33 into 6. 33 into 6. 33 into 6, it comes to 198. 198 plus 4 into 14. 4 into 14, it comes to 56. So 56 plus 198, it comes to 254. That's it. Now 6 into 0 is 0. 4 into 1 is 4. 6 into 1 is 6. 4 into 0 is 0. So here remains 6. So here, carefully you see here. 6 into minus 3 by 5. 6 3 is 18. So minus 18 divided by 5. Plus. Here 4 into 1 by 5. So 4 by 5. So LCM if we take 5. So minus 18 plus 4. So it will become minus 14 by 5. So here comes minus 14 by 5. Here 6 into 1 by 5 is 6 by 5. Plus into minus will become minus. 4 2s are 8. 8 by 5. If we take the LCM 5, 6 minus 8. 6 minus 8 is minus 2 by 5. So here you take minus 2 by 5. That's it. So we got the values of Zj. Now finally we need the index row elements. Cj minus Zj. So here 4 minus 4, 0. Then 6 minus 6, 0. 0 minus minus 14 will become plus 14. Plus 14 by 5. Again I repeat. 0 minus minus 14 by 5. So minus into minus will become plus. So 0 plus 14 by 5 is nothing but 14 by 5. Similarly, 0 minus, here minus 2 by 5. So minus into minus will become plus. 0 plus 2 by 5 is 2 by 5. That's it. Though finally, index row elements, the optimality test says all the values should be zeros and positives. And we got zeros and positive. We don't have any negative value. So this solution is the optimum solution. This solution is the optimum. No need to make any other improvement. If you make improvement, the cost will increase. Our objective is to minimize the cost. The minimum cost is 254. So finally, after making this table, you should write the conclusion. I'm not writing, I'm dictating, you note it down. Since all the index row elements are zeros and positives, so we reached the optimum solution. The optimum solution is x1 is equal to, how much is x1 here? 14. x2 is equal to 33. and the minimum cost is equal to 254. This 254 is the minimum cost. So what is x1 and x2? x1 is the number of units of compound A to be produced. And so how many units of compound A? 14 units of compound A should be produced and 33 units of compound B should be produced, so that the total cost will be minimum at 254. That's all. This is the first problem on minimization type. Remember, these two problems are a little bit difficult to understand in the first attempt itself. It will require some practice. So watch the video 2-3 times and practice yourself. Then only you can be able to get the command. Inshallah, we'll continue the next problem in the next video.